So in this video, I want to talk about the other type of collisions, the other extreme case of collisions that we'll cover in this course, and that is perfectly elastic collisions. So unlike the inelastic ones, which stick together, perfectly elastic collisions bounce off of each other. So we have, as shown in this picture here, we have a before the collision and we have an after collision. And before the collision, we have mass 1 traveling off to the right, and we have mass 2 traveling off to the left. After the collision, they have bounced off of each other such that mass 2 is now headed off to the right, and mass 1 is headed off to the left. So they have bounced off of each other, the opposite of the inelastic collisions, which they stuck together. Now, in this collision, and like all collisions, the momentum is conserved. So we have our initial momentum is equal to the final momentum still. But in this case, since they're not stuck together, we have to use the definition that we gave for conservation of momentum before, in which case we have mass A, velocity A plus mass B, velocity B initial is equal to mass A, velocity A plus mass B, velocity B final. They don't stick together, so they don't have the same final velocity. So we have to use this formulation for the conservation of momentum. Now, just like the inelastic collisions, there are no truly perfectly elastic collisions in nature. They're partially inelastic or partially elastic, because in a perfectly elastic collision, we'll discuss this in more detail in a minute, in a perfectly elastic collision, kinetic energy is also conserved. In the inelastic collision, kinetic energy was lost. But in an elastic collision, kinetic energy is conserved, meaning that it remains the same before and after. So we don't have any cases where that actually happens in nature, but there are some that are fairly close, like playing pool. You have the cue ball here. When it strikes all the other balls, it sends them off and they bounce right off of each other. Now, in reality, there is a little bit of noise generated here, right? And this noise is a form of energy. So some of the kinetic energy that was in this cue ball was transferred to sound energy during this collision. But it's this type of collision here with a cue ball with other balls is pretty close to perfectly elastic. Okay, so in perfectly elastic collisions, we have a picture shown here. We have our system of interest here, and we have the net force is equal to 0 because it's on a frictionless surface, so we can say that momentum is conserved. So momentum is conserved, so we have this equation up here. This is our conservation of momentum, but we also have kinetic energy conserved. So this means that the kinetic energy in the first case, KE1, KE2, is equal to the same as the collision after. So they said KE prime, this is prime 1, and KE prime 2. Or we can say, writing it out here, the change in kinetic energy is equal to 0. So the kinetic energy in the final condition is equal to the kinetic energy in the initial condition. And the kinetic energy of the system is the sum of the kinetic energy of the individual pieces. So we have here the kinetic energy. This is going to be kinetic energy of A plus the kinetic energy of B, and the final condition is equal to the kinetic energy of A plus the kinetic energy of B in the initial condition. So what this comes down to is that 1/2 mass of A times the velocity of A squared plus 1/2 mass of B times the velocity of B squared in the final condition is equal to 1/2 mass of A velocity of A squared plus 1/2 mass of b, velocity of b squared in the final condition. This is our conservation of kinetic energy for a perfectly elastic collision. So this is true in any perfectly elastic collision. And this, combined with our conservation of momentum up here, so taking this one, combining it with this one, creates two fairly large equations, but this is a system of equation in which we can solve for any elastic collision. So we have two equations, so we can have two unknowns. So there's more that we can solve for if we know the collision is perfectly elastic. And I'll spare the algebra in this video, but this actually simplifies down to a fairly nice equation relating the difference in the initial velocities and the final velocities. What this simplifies down to is that VB final, so the velocity of object B in the final condition minus the velocity of object A in the final condition, is negative of the velocity of A. Oops, sorry. I have to be careful that we use the same. We have to use the same order. Minus, it's the negative of the velocity of B in the initial minus the velocity of A in the initial. So what this says, and you can write this many different ways, is that the difference in the velocities in the final condition is negative of the difference in the velocities in the initial condition. So if I wanted to, this is exactly the same as saying here VA initial minus VB initial is equal to negative of VA final minus VB final. And I might write it different ways in lecture, as long as the difference in the velocities in one condition, the initial or final, is negative of the difference in the velocities in the other condition. Okay? Now this is what it simplifies down to. One thing you have to be very careful with here is that the velocity is a vector, right? So if this is, say, VB final is a -3 or something like that, and VA final is, 2, then this becomes 2 minus a -3, so this is equal to 5. Just, you have to be very careful with your sign convention in your velocities in this case. So with these two put together, we have, for any perfectly elastic collisions, so in elastic collisions, so in elastic collisions, not inelastic, we have conservation of momentum. So we have here MA VA plus MB VB initial is equal to MA VA plus MB VB final, and we also have VB final minus VA final is equal to negative of VB initial minus VA initial. We have these two equations that we solve simultaneously, and we can solve for two unknowns. Generally, as you see, there's less variables in the second one here, so generally you want to solve this one first and then plug your results in to the upper one, but different circumstances require different methodologies. So for perfectly elastic collisions, we have both of these equations we can use, because in a perfectly elastic collision, not only is momentum conserved, as it is in every collision, but kinetic energy is also conserved.